In 1997, a satellite detected a flash of energy from across the universe that released more power in 10 seconds than our Sun will produce in its entire 10 billion year lifetime. The source was not a supernova. It was not a colliding galaxy. It was something far more violent, something so extreme that for a brief moment it outshone everything else in the observable cosmos combined. Scientists call them gamma ray bursts, and they sit at the absolute ceiling of what the universe permits. No explosion ever directly observed comes close. Not the death of giant stars. Not the collision of neutron stars. Nothing. This is the story of how we found them, why they happen, and what they reveal about the hard limits of cosmic violence. The answer will change how you see every star in the night sky. If you enjoy journeys through the most extreme corners of the universe, consider tapping that like button and subscribe. Now, get yourself comfortable. Let's begin. Every star you have ever seen is fighting a war. Not a metaphorical war, a literal, physical, measurable conflict between two forces that have been locked in combat since the moment each star ignited. On one side is gravity, relentless, patient, crushing. It wants to compress every atom of stellar material into the tightest possible space. On the other side is the outward pressure generated by nuclear fusion, the energy released when hydrogen atoms slam together at tens of millions of degrees and fuse into helium, releasing photons that push back against the inward crush. These two forces balance each other with extraordinary precision. That balance is what a star is. A sphere of plasma held in equilibrium between collapse and explosion. For millions or billions of years, depending on the star's mass, this balance holds. Light radiates outward. Planets orbit. The universe appears calm. Then the fuel runs out. And gravity, which has been waiting since the very first second of the star's existence, finally wins. What happens next is one of the most violent events in the known cosmos. For massive stars, those born with at least 8 times the mass of our Sun, the end comes not as a slow fade but as a catastrophic implosion, followed by a rebound so energetic it can briefly outshine an entire galaxy. Scientists call this event a supernova. For centuries, supernovae were considered the most powerful explosions the universe could produce. The numbers behind them are staggering enough to justify that belief. But the numbers also reveal something the early astronomers could never have guessed. Supernovae are not the ceiling. They are immense, but they are bounded. Something observed in the cosmos dwarfs them by orders of magnitude. To understand why, we need to follow a massive star through its entire life and into its death. We need to see exactly how the energy is produced, how much is released, and why that amount, extraordinary as it is, hits a wall it cannot climb past. A star like our Sun fuses hydrogen into helium in its core for roughly 10 billion years. It is a steady, predictable process. The Sun converts approximately 4 million tons of matter into pure energy every second through Einstein's mass-energy equivalence, producing a luminosity of about 3.8 times 10 to the 26 watts. It has been doing this for 4.5 billion years and will continue for another 5 billion. The Sun is a marathon runner. Massive stars are sprinters. A star born with 25 times the Sun's mass burns through its hydrogen fuel not in billions of years but in roughly 7 million. The reason is straightforward. A more massive star has stronger gravitational compression at its core, which drives temperatures and pressures high enough to accelerate the fusion rate enormously. Fusion scales steeply with temperature. Double the core temperature and the fusion rate does not merely double, it increases by a factor of thousands. Massive stars live fast because they burn fast, and they burn fast because gravity squeezes them harder. But hydrogen is only the first course. When the hydrogen in the core is exhausted, the core contracts under gravity, heats up further, and begins fusing helium into carbon and oxygen. This phase lasts roughly 500,000 years for a 25 solar mass star. When the helium runs out, the core contracts again, heats up again, and begins fusing carbon into neon and magnesium. This phase lasts perhaps 600 years, then neon burning roughly 1 year, then oxygen burning approximately 6 months, then silicon burning a single day. Each successive fuel source is less efficient and lasts a shorter time. The star develops an onion-like structure with concentric shells of different elements burning at different rates. Iron accumulates in the core like ash in a furnace, and iron is where the road ends. Unlike every element that came before it, iron cannot release energy through fusion. Fusing iron requires energy rather than producing it. The moment the core fills with iron, the star has no remaining energy source to resist gravitational collapse. What follows is measured not in years or days, but in milliseconds. The iron core, roughly 1.5 times the mass of our Sun, compressed into a sphere about the size of Earth, collapses under its own gravity, at speeds approaching 70,000 kilometers per second, roughly a quarter of the speed of light. In less than a second, the core compresses from Earth-sized to city-sized, roughly 20 kilometers across. The density reaches values exceeding 100 trillion times the density of water. At these conditions, protons and electrons are crushed together to form neutrons, releasing a flood of neutrinos. The core becomes a neutron star, a ball of nuclear matter so dense that a teaspoon of it would weigh approximately 6 billion tons on Earth's surface. The collapse does not stop gently. The core overshoots its equilibrium density, compresses beyond what the strong nuclear force can tolerate, and then rebounds like a compressed spring. This rebound sends a shockwave outward through the infalling stellar material. For a brief time, the shockwave stalls. The infalling outer layers slam into it, sapping its energy. But the neutrinos pouring out of the newborn neutron star deposit a small fraction of their energy into the material behind the shock, roughly 5% of the total neutrino energy. And this injection revives the shockwave, driving it outward through the star's remaining envelope. The outer layers are blown apart. A supernova is born. The total energy released during this process is approximately 3 times 10 to the 46 joules. To be precise, this figure represents the gravitational binding energy liberated during the formation of the neutron star. The vast majority of this energy, roughly 99%, is carried away by the neutrino burst that accompanies core collapse. These ghostly particles interact with matter so weakly that they stream through the star's outer layers as though the material were not there, escaping into space within seconds. The remaining 1% of the energy, still an enormous figure of approximately 10 to the 44 joules, goes into the kinetic energy of the expanding ejector and the visible light that astronomers observe. Let us try to anchor that number in something tangible. Our Sun produces approximately 3.8 times 10 to the 26 joules every second. To match the total energy released by a single supernova, the Sun would need to burn at its current rate for roughly 2.5 billion years. But a supernova releases that energy in seconds. The peak luminosity of a core collapse supernova can reach 10 billion times the luminosity of the Sun, making it bright enough to outshine the combined light of every other star in its host galaxy for several weeks. Yet we need to pause here and establish a distinction that will be critical for everything that follows. There are 3 different ways people describe how impressive a cosmic explosion is, and these 3 ways do not measure the same thing. Confusing them leads to wildly inaccurate conclusions. The first is total energy released. This counts every joule of energy produced by the event across all forms: visible light, kinetic energy of ejected material, neutrinos, gravitational waves, X-rays, radio waves. It measures the true physical violence of the explosion. This is the metric that matters when we ask what the most powerful explosion in the universe is. The second is peak luminosity, or apparent brightness. This describes how bright something appears at a particular moment, often from a particular viewing angle. An event can appear blindingly luminous from one direction and relatively dim from another if its energy is focused into a narrow beam. An event can also have a modest total energy budget but appear extremely bright for a fleeting instant because it concentrates its emission into a tiny window of time. The third is physical size or scale. Some explosions span enormous volumes. A supernova remnant can eventually stretch across dozens of light years. But spatial extent does not determine power. A firecracker is smaller than a campfire, but nobody would claim a campfire is more explosive. Throughout this story, the question we are answering is this: what is the most powerful explosion ever directly observed in the universe, measured by total energy released? Not the brightest in apparent magnitude, not the largest in physical diameter, the most powerful. That is the only honest way to compare cosmic explosions. The history of supernova observation gives this question personal weight. Humans have been watching stars explode for nearly 1,000 years. In the year 1054, astronomers in China and likely in the Arab world and among the ancestral Puebloans of what is now the American Southwest documented a brilliant new star that appeared in the sky near the constellation we call Taurus. It was bright enough to see in broad daylight for 23 consecutive days and remained visible to the naked eye at night for nearly 2 years before fading. That event created what we now call the Crab Nebula, a 6 light-year wide cloud of expanding debris still glowing nearly a millennium later. At its heart sits a pulsar, a rapidly spinning neutron star rotating roughly 30 times per second, sweeping beams of radiation across space like a lighthouse. In 1572, Tycho Brahe turned his instruments toward another brilliant newcomer in the constellation Cassiopeia. His meticulous measurements of the star's changing brightness and position helped dismantle the ancient Aristotelian belief that the heavens beyond the moon were fixed and eternal. Here was proof that the cosmos could change, violently and without warning. 32 years later, in 1604, Johannes Kepler observed yet another supernova, the last to be visible to the naked eye from within our own galaxy. 4 centuries have passed since, and we are statistically overdue for the next one. But the true revolution in understanding supernova energetics came not from optical observation but from a detection nobody expected to make with the instruments available at the time. On February 23rd, 1987, a blue supergiant star called Sanderlic -69202 exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way lying approximately 168,000 light-years from Earth. The event, designated SN 1987A, was the closest observed supernova since Kepler's sighting nearly 400 years earlier. SN 1987A produced something unprecedented: the first confirmed detection of neutrinos from a stellar explosion. 3 underground detectors, Kamiokande II in Japan, the Irvine, Michigan Brookhaven detector beneath Lake Erie in the United States, and the Baksan Neutrino Observatory in the Soviet Union registered a combined total of approximately 24 neutrinos arriving over a span of about 13 seconds. The number sounds laughably small, 25 particles, but consider the physics. Neutrinos are so reluctant to interact with matter that roughly 65 billion of them from our own sun pass through every square centimetre of your skin every second without touching a single atom. Detecting even 25 from an event 168,000 light-years away required enormous underground tanks filled with thousands of tons of ultra-purified water shielded from cosmic ray interference by hundreds of meters of rock. Those 24 detections confirmed that the core collapse had released approximately 3 times 10 to the 46 joules of energy in neutrinos alone, matching theoretical predictions with startling precision. It was one of the great triumphs of 20th century astrophysics. SN 1987A also surprised scientists by revealing that blue supergiants could explode as supernovae. Prior models predicted that only red supergiant stars in the final bloated phase of their evolution would undergo core collapse. Sanderlic -69202 had been a compact, hot blue star, not the swollen red giant everyone expected. The discovery forced major revisions to stellar evolution theory and demonstrated that massive stars follow more varied pathways to death than anyone had assumed. Today, decades later, the remnant of SN 1987A continues expanding and evolving. The Hubble Space Telescope and the James Webb Space Telescope have imaged a glowing ring of material around the explosion site gas, expelled by the progenitor star in the tens of thousands of years before its death, now being slammed and illuminated by the supernova blast wave. These observations provide a real-time laboratory for studying how supernovae interact with their surroundings and seed interstellar space with heavy elements. That seeding process is not a minor footnote, it is the reason you exist. Every element heavier than iron on the periodic table, gold, platinum, uranium, iodine, was produced primarily in the extreme conditions of supernovae and related events. The lighter heavy elements up to and including iron were forged inside the star during its lifetime and then scattered into space by the explosion. The calcium in your bones was manufactured inside a star that died before our solar system formed. The iron carrying oxygen through your bloodstream was forged in a stellar core that collapsed billions of years ago. Without supernovae, there would be no rocky planets, no complex chemistry, no biology. The violence of stellar death is, paradoxically, the prerequisite for everything we consider alive. Supernovae come in distinct categories, and understanding these categories helps illuminate why their energy is bounded. Core collapse supernovae, the type we have been discussing, result from the gravitational implosion of massive stars. Within this family, Type 2 supernovae retain their hydrogen envelopes and show hydrogen spectral lines. Type IB supernovae have lost their hydrogen layers but retain helium. Type IC supernovae have been stripped of both hydrogen and helium, leaving a bare carbon-oxygen core exposed. The stripping occurs through powerful stellar winds or through gravitational interaction with a binary companion star that peels away the outer layers over millions of years. A completely separate class exists, Type Ia supernovae. These do not involve core collapse at all. Instead, they occur in binary star systems, where a white dwarf, the compact remnant of a low to intermediate mass star, accretes material from a companion until its mass exceeds the Chandrasekhar limit, approximately 1.4 solar masses. At this threshold, electron degeneracy pressure can no longer support the white dwarf against gravitational collapse. The result is not a collapse into a neutron star, but a runaway thermonuclear detonation that destroys the entire white dwarf in a matter of seconds. The explosion releases approximately 1 to 2 times 10 to the 44 joules in kinetic energy, substantial, but notably less than the total energy of a core collapse supernova. Type Ia events are enormously important in cosmology because their consistent peak luminosity makes them reliable standard candles for measuring cosmic distances. They were the tools that revealed the accelerating expansion of the universe in 1998. But in terms of raw explosive power, they rank below core collapse events. Here is where we encounter the ceiling. Among core collapse supernovae, the total energy released is remarkably consistent from event to event. Whether the progenitor star was 9 solar masses or 40 solar masses, the gravitational binding energy liberated during neutron star formation clusters around 3 times 10 to the 46 joules. The reason is that neutron star properties are governed by nuclear physics, not by the progenitor's total mass. The core that collapses is always roughly 1.5 solar masses, the Chandrasekhar mass, and it always compresses to roughly the same density and radius. The gravitational potential energy release depends on the mass and final radius of the neutron star, both of which are constrained by the equation of state of nuclear matter. You cannot make a significantly more energetic supernova simply by starting with a more massive star. The energy ceiling is built into the physics of neutron degeneracy. Some supernovae appear dramatically more luminous than average. Events classified as superluminous supernovae can outshine typical supernovae by factors of 100 or more at peak brightness. But luminosity and total energy are not the same thing. Many superluminous events achieve their extreme brightness through a process called circumstellar interaction. The supernova ejecta slam into dense shells of material surrounding the star gas expelled in violent episodes during the final years or decades of the progenitor's life. The collision converts kinetic energy into visible light with extraordinary efficiency, creating a brilliant display without actually increasing the total energy budget. The energy was always there in the kinetic motion of the debris. The interaction merely converts it into photons that telescopes can see. Other superluminous events may be powered by magnetars rapidly spinning neutron stars, with magnetic fields reaching 10 to the 15 Gauss, roughly a quadrillion times stronger than Earth's magnetic field. A newborn magnetar can inject its rotational energy into the expanding supernova debris over weeks, boosting the light curve far above what the explosion alone would produce. But the available rotational energy of even the most extreme magnetar is limited by its mass and spin rate to approximately 10 to the 45 joules. Impressive, but finite, and still within the broader energy envelope of neutron star formation. The point is inescapable. Supernovae are extraordinary events. They outstrip every terrestrial phenomenon, every nuclear weapon, every volcanic eruption, every asteroid impact by factors so large that meaningful comparison becomes impossible. The energy released in a single core collapse supernova exceeds the total energy output of our Sun over billions of years. A supernova can briefly outshine 10 billion stars. Its debris enriches the cosmos with the heavy elements necessary for planets and life. By every human standard, a supernova is an apocalypse of incomprehensible scale, and yet it is not the most powerful explosion ever observed. Not even close. The energy of a supernova is capped by the physics of neutron star formation at approximately 3 times 10 to the 46 joules. This is a hard limit, enforced by the fundamental properties of nuclear matter. The visible and kinetic energy, the part that actually does destructive work on surrounding material, is roughly 1% of that total, around 10 to the 44 joules. These are immense numbers. But the universe has produced events that exceed the kinetic and radiative output of supernovae by factors of 100. Events that make a supernova look restrained by comparison. The path to those events begins with a question. What happens when the collapsing core is too massive to form a neutron star? What happens when instead of bouncing, the core keeps falling past the neutron star stage, past any known state of matter, falling until space itself closes around it and a black hole forms? What happens when the dying star is not just massive, but rapidly rotating, and the angular momentum of the collapse creates something a simple spherical implosion never could? The answer is that you get something rarer, something more violent, and something far more energetic than any ordinary supernova. You get an explosion that bridges the gap between the deaths of stars and the most extreme phenomena the cosmos has ever produced. The supernova was the floor. The next level awaits, and even that next level, remarkable as it is, will ultimately fall short of the true ceiling of cosmic violence. On April 25, 1998, a satellite orbiting Earth detected a pulse of gamma radiation lasting approximately 25 seconds. The burst, catalogued as GRB 980425, was modest by the standards of gamma-ray burst astronomy, relatively faint, relatively brief, and initially unremarkable. But within days, optical telescopes pinpointed the source to a spiral galaxy called ESO 184G82, located approximately 140 million light-years away. When astronomers trained their instruments on that location, they found a supernova, and it was unlike anything they had ever seen. The supernova was designated SN 1998BW. Its spectral lines were grotesquely broadened, smeared out across wavelengths, in a way that indicated the ejected material was moving at velocities approaching 30,000 kilometers per second. That is roughly 1/10 the speed of light. Ordinary supernovae eject their material at 3 to 5% of light speed. Whatever had happened to this star, it had happened with far more violence than standard stellar death could explain. The peak luminosity was approximately 10 times greater than a typical Type IC supernova. The kinetic energy implied by the expansion velocities calculated by combining the measured speeds with estimates of the ejected mass came out to roughly 3 times 10 to the 45 joules. Compare that to the roughly 10 to the 44 joules of kinetic energy released by an ordinary core collapse supernova. SN 1998 BW carried 30 times more kinetic punch. In a field where energy differences of a factor of 2 prompt serious theoretical investigation, a factor of 30 demanded an entirely new category. Scientists gave that category a name. They called it a hypernova. The term had been floated earlier in theoretical discussions, but SN 1998 BW gave it observational teeth. Here was proof that some stellar deaths operated in a fundamentally more energetic regime than anything previously documented. And the connection to a gamma-ray burst, however faint, that particular burst was hinted at a relationship between these extreme explosions and the most mysterious high-energy phenomena in the cosmos. That hint would eventually become a certainty, but in 1998, the full picture was still emerging. In fact, the picture was considerably more contentious than that measured statement suggests. The association between SN 1998 BW and GRB 980425 was immediately controversial. The problem was that GRB 980425 was extraordinarily faint by the standards of gamma-ray burst astronomy. If it truly originated at the distance of SN 1998 BW, a mere 140 million light-years, practically next door in cosmological terms, then its total energy in gamma rays was roughly 10,000 times weaker than a typical cosmological gamma-ray burst. That enormous discrepancy troubled many researchers. Some argued the spatial coincidence was exactly that, a coincidence. A random gamma-ray burst somewhere in the background or foreground had happened to go off at the same time and in roughly the same direction as an unusual supernova. The probability was small, but the alternative that gamma-ray bursts could span a range of luminosities covering 4 or 5 orders of magnitude seemed equally problematic. The debate split the community. Supporters of the association pointed to the precise spatial and temporal alignment between the burst and the supernova, arguing that the odds of such a coincidence were vanishingly low. Skeptics pointed to the energy discrepancy and asked whether a single underluminous case could really establish a physical connection between two phenomena that had never before been observed together. Papers were published arguing both sides. Conferences held dedicated sessions where researchers presented the same data and arrived at opposite conclusions. For 5 years, the question hung unresolved, and during that time, the supernova gamma-ray burst connection remained one of the most tantalizing but unproven hypotheses in high-energy astrophysics. The resolution came on March 29, 2003, when a gamma-ray burst designated GRB 030329 erupted from a galaxy approximately 2.6 billion light-years away. This burst was bright genuinely, unambiguously bright, with an isotropic equivalent energy firmly in the range of classical cosmological gamma-ray bursts. Its optical afterglow was detected within hours, and it was luminous enough that even modest telescopes could track its evolution. Then, as the afterglow faded over the following weeks, a familiar spectral signature emerged underneath the declining light. Broad absorption lines, extreme expansion velocities. The unmistakable fingerprint of a hypernova. The supernova was designated SN2003DH, and its spectral match to SN 1998 BW was striking the same grotesquely broadened features, the same kinetic energies exceeding 10 to the 45 joules, the same class of stripped envelope explosion. Here, at last, was the evidence the field had been waiting for. Not an ambiguous underluminous burst at a nearby distance, but a powerful, cosmologically distant gamma-ray burst with a hypernova buried inside it. The connection was no longer a statistical argument about one peculiar case. It was a direct, repeatable observation. The gamma-ray burst community, after half a decade of argument, converged on a conclusion that would reshape the field. At least some long-duration gamma-ray bursts were produced by the deaths of massive stars, and the explosions accompanying those deaths were far more violent than ordinary supernovae. The mechanism behind this connection, how a stellar collapse could simultaneously produce a hypernova, visible from every direction, and a gamma-ray burst, visible only along a narrow axis, required a theoretical framework that had been developing in parallel with the observations. To understand what separates a hypernova from an ordinary supernova, we need to focus on the progenitor star and, critically, on what its core is doing at the moment of collapse. Not all massive stars are created equal. A star born with 12 solar masses and a star born with 50 solar masses both end their lives in gravitational collapse, but the conditions at the moment of implosion differ dramatically, and those differences determine whether the result is a standard supernova or something far more extreme. The crucial variable is the mass of the collapsing core. In Part 1, we saw that most core collapse supernovae produce neutron stars, compact remnants supported against further collapse by the pressure of neutrons packed at nuclear density. The formation of that neutron star liberates a fixed amount of gravitational binding energy, approximately 3 × 10⁻46 joules, and the resulting bounce drives the supernova shockwave. But neutron stars have a maximum mass. Above roughly 2 to 2.5 solar masses, the precise value depends on the still uncertain equation of state of ultradense matter. No amount of neutron degeneracy pressure can resist gravity. The core does not bounce. It does not stabilize. It keeps collapsing, passing through the neutron star stage entirely until a black hole forms. This changes everything about the explosion. When a black hole forms instead of a neutron star, there is no hard surface to generate a clean rebound. The core does not bounce in the traditional sense. Instead, the dynamics are governed by how material falls into the newly formed black hole and whether any mechanism can extract energy from that infall before the material vanishes behind the event horizon. For a non-rotating or slowly rotating core, the answer is grim. Material falls in, the black hole grows, and very little energy escapes. You might not get an explosion at all, just a quiet disappearance called a failed supernova, where the star collapses and vanishes from the sky without fanfare. But for a rapidly rotating core, the physics changes radically. Angular momentum, the rotational equivalent of linear momentum, prevents material from falling directly into the black hole. Instead, in falling, material spirals inward, forming a dense, hot accretion disk surrounding the black hole. This disk is not a passive structure. It is a furnace. Gravitational potential energy is converted into thermal energy as material spirals deeper into the gravitational well. Friction within the disk heats it to billions of degrees. Magnetic fields, amplified by the differential rotation of the disk, inner regions orbiting faster than outer regions, wind up into enormously powerful configurations. The conditions inside this disk are difficult to convey without losing either accuracy or impact, but they are worth dwelling on, because this is the engine room of the most powerful explosion in the universe. The inner regions of the accretion disk orbit the black hole at a significant fraction of the speed of light. Material at the innermost stable orbit completes a full revolution in milliseconds. The temperature in these inner regions reaches up to 100 billion degrees hotter than the core of the Sun by a factor of nearly 10,000, comparable to the most extreme temperatures found anywhere in the universe outside the first moments after the Big Bang. The density is extreme, not as dense as the neutron star cores discussed in Part 1, but dense enough that nuclear reactions occur freely in the disk material, producing copious neutrinos that carry energy away and alter the chemical composition of the infalling matter. The energy density in the inner disk beggars comparison with anything in normal astrophysics. The energy contained in each cubic centimeter of this region, combining thermal energy, magnetic energy, radiation pressure, and the kinetic energy of orbital motion, exceeds the energy density at the center of our Sun by factors of trillions. The disk contains solar masses of such material, all of it spiraling inward, all of it converting gravitational potential energy into heat and radiation, and magnetic fury as it falls. The entire process unfolds on a timescale that seems absurd for an event of this magnitude. The accretion disk consumes material at a rate of up to 1/10 of a solar mass per second, and in some models, several times that. To appreciate what even the lower figure means, 1/10 of the Sun's mass, devoured and processed in the time it takes to draw a single breath. No other known astrophysical process operates at this rate. Even the most voracious supermassive black holes at the centers of active galaxies, consuming entire stars over weeks and months, are leisurely by comparison. The collapsar disk is a brief, all-consuming frenzy, a few solar masses of material processed through the most efficient energy extraction mechanism in the universe in a span of seconds to minutes. When the available material is exhausted, the central engine shuts down, the jets it powered begin to coast on their own momentum, and the event is effectively over. The window of extreme energy production is brief, but what emerges from that window is unlike anything else in the observed universe. The magnetic field amplification within the disk is equally remarkable. Differential rotation winds the field lines tighter with each orbit, amplifying the magnetic energy density until it approaches equipartition with the thermal and kinetic energy of the disk material. At this point, the magnetic field is no longer a minor player in the dynamics. It becomes a structural element of the system, capable of redirecting bulk flows of plasma, extracting rotational energy from the black hole itself, and channeling vast quantities of energy along the rotational axis where the field lines converge. It is this magnetically dominated funnel, collimated by the geometry of the disk and the rotation of the black hole, that gives birth to the jets. These amplified magnetic fields do something remarkable. They extract energy from the disk and from the spinning black hole itself, channeling it into two narrow jets of material that shoot outward along the black hole's rotation axis. At velocities approaching the speed of light, the jets are not gentle outflows, they are ultra-relativistic cannons, accelerating plasma to Lorentz factors of 100 or more, meaning the material moves at more than 99.9% of the speed of light. The energy concentrated in these jets dwarfs the kinetic energy of an ordinary supernova shockwave. Simultaneously, the rest of the collapsing star that is not captured by the jets or swallowed by the black hole is blasted apart by a combination of the disk's energy output and the disruption caused by the jets punching through the stellar envelope. This quasi-spherical component of the explosion is the hypernova, the visible, broadly detectable part of the event that astronomers can observe from any viewing angle. This framework is called the collapsar model, and it was first articulated in detail by astrophysicist Stan Woosley in 1993, with significant contributions from Andrew McFadyen and other collaborators in the years that followed. The model elegantly explains both hypernovae and their more extreme manifestation gamma-ray bursts as different observable aspects of the same underlying catastrophe. The hypernova is the spherical explosion you see from any direction. The gamma-ray burst is the collimated jet you see only if you happen to be looking down the barrel. For the collapsar model to work, the progenitor star must satisfy several demanding conditions. First, it must be massive enough that its core exceeds the maximum neutron star mass at the moment of collapse, driving black hole formation rather than neutron star formation. This generally requires a progenitor born with at least 30 to 40 solar masses, though the exact threshold depends on how much mass the star loses during its lifetime through stellar winds. Second, the star must have shed its outer hydrogen and helium envelopes before collapse. If the envelopes remain, they present too much material for the jets to punch through. The jets stall inside the star, their energy thermalized and absorbed, and no gamma-ray burst escapes. The progenitor must be a stripped star, what astronomers call a Wolf-Rayet star, exposing its bare carbon-oxygen core. Wolf-Rayet stars deserve a moment of attention because they are among the most extreme objects in stellar astronomy, and almost nobody outside the field has heard of them. A typical Wolf-Rayet star retains between 10 and 50 times the mass of the Sun, having already shed a substantial fraction of its birth mass, and its surface temperature ranges from roughly 30,000 to over 200,000 degrees, making even the coolest Wolf-Rayet stars several times hotter than the Sun's surface. They radiate with a luminosity hundreds of thousands of times greater than solar. If you replace the Sun with a Wolf-Rayet star, the Earth would not merely be uninhabitable, it would be sterilized, its atmosphere stripped, its surface reduced to molten slag within hours. But the defining feature of a Wolf-Rayet star is not its brightness. It is its self-destruction. These stars drive winds of such ferocity that they lose mass at rates roughly 1 billion times greater than the solar wind. Material streams off the surface at speeds of 1,000 to 3,000 kilometers per second, fast enough to cross the distance from the Earth to the Moon in a few minutes, carrying away a significant fraction of the star's remaining mass over just a few 100,000 years. The expelled material forms vast glowing nebulae surrounding the star shells and bubbles of ionized gas that can span dozens of light years, sculpted into filaments and arcs by the relentless outflow. Hubble images of Wolf-Rayet nebulae reveal some of the most visually dramatic structures in the galaxy, yet these are merely the discarded outer layers of a star that is eating itself alive from the outside in. The spectra of Wolf-Rayet stars are instantly recognizable. Where most stellar spectra show narrow absorption lines, dark notches, where specific wavelengths of light are absorbed by the stellar atmosphere, Wolf-Rayet spectra are dominated by broad, bright emission lines. The lines are broadened by the Doppler effect of material moving at enormous speeds in every direction, and they glow in emission rather than absorption because the wind itself is so hot and dense that it radiates copiously. Astronomers classify Wolf-Rayet stars into subtypes based on which emission lines dominate. WN stars show strong nitrogen lines, while WC and WO stars show carbon and oxygen, reflecting how deeply the stellar winds have excavated into the products of nuclear burning. A WC or WO star has been stripped all the way down to the layers where helium burning has converted the original material into carbon and oxygen, precisely the bare core that the collapsar model requires. By the time a Wolf-Rayet star reaches the end of its nuclear fuel, it has been stripped down to its essential core, a dense, compact ball of carbon and oxygen, sometimes with a thin shell of helium, rotating rapidly and radiating furiously. It is a star that has spent its final millennia tearing itself apart. What remains is precisely the object the collapsar model requires, a bare, massive, rapidly evolving core with no bloated envelope to cushion or impede the catastrophe that is about to unfold. The violence of the death, in a very real sense, was made possible by the violence of the life that preceded it. Third, and most critically, the core must be rotating rapidly at the moment of collapse. This is the requirement that makes hypernovae rare. Most massive stars are born rotating rapidly, but they lose angular momentum throughout their lives. Stellar winds carry material away from the surface, and that material takes angular momentum with it. Magnetic coupling between the stellar core and envelope can transfer angular momentum outward, slowing the core's rotation. By the time a typical massive star reaches core collapse, its core rotates far too slowly to form an accretion disk. It collapses more or less spherically, forms a neutron star or a quietly swallowed black hole, and that is that. Only a small fraction of massive stars maintain sufficient core rotation to power the collapsar mechanism. How they achieve this is one of the most actively studied questions in stellar astrophysics. Several pathways have been proposed. One involves binary star systems. A massive star in a close binary can be tidally locked to its companion, meaning gravitational interactions force the star to rotate in synchrony with its orbital period. If the orbital period is short enough, this imposed rotation can keep the stellar core spinning rapidly, despite the braking effects of winds and magnetic fields. Additionally, mass transfer between binary companions can spin up a star material accreted from a companion carries angular momentum that is deposited into the receiving star, accelerating its rotation. Another pathway involves chemically homogeneous evolution. In stars with very low metallicity, meaning they contain very few elements heavier than helium, stellar winds are much weaker because the wind-driving mechanism depends on photon interactions with metal atoms in the stellar atmosphere. Fewer metals mean weaker winds, less mass loss, and less angular momentum loss. Under these conditions, rapid rotation can trigger a mixing process that keeps the entire star chemically homogeneous, rather than developing the layered onion shell structure of typical massive stars. The star evolves as a compact, hot, rapidly rotating object that retains its angular momentum all the way to core collapse. This pathway was likely more common in the early universe, when stellar metallicities were much lower than they are today. A third possibility involves stellar mergers. Two massive stars in a tight binary can spiral toward each other and merge, creating a single, rapidly rotating, very massive star. The merger injects enormous angular momentum into the resulting object, potentially setting the stage for a collapsar billions of years later when the merged star finally reaches the end of its nuclear fuel. Each of these pathways is plausible. Each has theoretical support from computer simulations of binary stellar evolution and single star evolution at low metallicity. But all of them require specific and somewhat unusual initial conditions, which explains why hypernovae are vastly rarer than ordinary supernovae. Estimates suggest that our galaxy produces roughly 1 to 2 core collapse supernovae per century, but a hypernova might occur only once every several 100,000 years in a Milky Way-sized galaxy. Some estimates push the interval even longer. These events are genuinely rare enough that no confirmed hypernova has ever been observed within our own galaxy in recorded history. The confirmed hypernovae that have been studied in detail all share a distinctive observational signature. They are classified as broad-lined type-Ike supernovae type-Ike because they lack hydrogen and helium in their spectra, confirming that the progenitor was a stripped star, and broad-lined because the extreme expansion velocities Doppler broaden the spectral features far beyond what normal supernovae produce. This spectral fingerprint has become the calling card of the hypernova class. SN 2003DH, associated with GRB 030329, provided the second major confirmation of the hypernova gamma-ray burst connection. This event occurred in a galaxy approximately 2.6 billion light-years away. Its relative proximity by gamma-ray burst standards allowed exceptionally detailed observations. Spectroscopic analysis revealed the same grotesquely broadened lines seen in SN 1998 BW, indicating expansion velocities exceeding 25,000 kilometers per second. The inferred kinetic energy was comparable, several times 10 to the 45 joules. The associated gamma-ray burst was much brighter than GRB 980425, confirming that the faintness of the earlier burst was an anomaly rather than a rule. SN 2006AJ, linked to GRB 060218, offered a different perspective. This event was closer, roughly 440 million light-years away, and somewhat less energetic than the prototypical hypernovae. Its kinetic energy was estimated at roughly 2 times 10 to the 45 joules, and its spectral lines, while broadened, were less extreme than those of SN 1998 BW. Some researchers classified it as a transitional object, sitting between ordinary energetic supernovae and full-blown hypernovae. Its existence suggested a continuum of explosion energies rather than a sharp boundary between the two classes. SN 2010BH, associated with GRB 100316D, reinforced this continuum picture. Located roughly 800 million light-years away, it displayed hypernova-class kinetic energies but somewhat lower peak luminosity. The diversity among confirmed hypernovae indicates that the collapsar mechanism operates across a range of core masses, rotation rates, and progenitor structures, producing a spectrum of outcomes rather than a single cookie-cutter explosion. The connection between hypernovae and heavy element production deserves attention here because it introduces genuinely new chemistry not present in ordinary supernovae. The extreme temperatures and densities in the accretion disk surrounding the newborn black hole create conditions for nucleosynthesis pathways that standard supernova shockwaves cannot access. In particular, the neutrino-driven winds from the hot inner disk produce conditions favorable for the synthesis of certain isotopes of nickel, zinc, and cobalt in ratios that differ markedly from ordinary supernova yields. This matters because astronomers can test the theory by examining the chemical fingerprints of ancient stars. The oldest, most metal-poor stars in the Milky Way's halo formed from gas enriched by the very first generations of stellar explosions. Their elemental abundance patterns record the types of explosions that occurred in the early universe. When researchers compare these observed patterns to the predicted yields of different explosion types, they find that standard supernova models alone cannot reproduce the observations. Adding a contribution from hypernovae, particularly for elements like zinc and cobalt, improves the match significantly. This chemical evidence independently supports the conclusion that hypernovae were more common in the early, low metallicity universe, consistent with the theoretical expectation that weaker stellar winds at low metallicity allowed more stars to retain the rapid core rotation needed for the collapsar mechanism. Now we must address the critical question of collimated versus isotropic energy release, because this concept is essential for understanding why hypernovae, despite their extraordinary power, still fall short of the most powerful observed explosions. An ordinary supernova radiates its energy roughly equally in all directions. If you place detectors at every point on a sphere surrounding the explosion, each detector receives approximately the same energy flux. This is isotropic emission. The total energy is the flux measured at any point multiplied by the area of the sphere. A hypernova is more complicated. The quasi-spherical component, the disruption of the stellar envelope, radiates roughly isotropically, just like a normal supernova but with more kinetic energy. This is the part that optical telescopes detect regardless of the observer's viewing angle, but the jets radiate very differently. They concentrate enormous energy into narrow cones, typically spanning only a few degrees on either side of the rotation axis. Imagine two identical flashlights, each containing the same battery. One has a wide-angle lens that spreads its light across an entire room. The other has a narrow beam lens that focuses all its light into a tight spotlight. If you stand in the spotlight beam, the narrow flashlight appears enormously brighter than the wide-angle one, even though both contain the same total energy. The narrow beam concentrates its power into a smaller area, creating an illusion of greater total output for anyone standing in the beam's path. Gamma-ray burst jets work on this same principle, scaled up by a factor of 10 billion trillion. The energy in the jet is real and enormous, but is not distributed evenly across the sky. An observer looking directly down the jet axis sees something that appears fantastically more energetic than the same event viewed from the side. This viewing angle dependence means that the measured brightness of a gamma-ray burst depends critically on whether Earth happens to lie within the jet's narrow cone. For hypernovae specifically, the jets are present but often less powerful or less narrowly collimated than in the most extreme gamma-ray bursts. Some hypernovae produce jets that successfully break through the stellar envelope and generate observable gamma-ray bursts. Others produce jets that stall inside the star, depositing their energy into the stellar material and boosting the spherical explosion's kinetic energy without producing a detectable gamma-ray burst. These choked jet hypernovae appear as unusually energetic supernovae from the outside, but reveal their jet-driven origin through their aspherical debris structures and extreme expansion velocities. The energy budget of a hypernova, combining the quasi-spherical explosion and the jet contribution, typically falls in the range of 10 to the 45 to 10 to the 46 joules in kinetic energy. The neutrino component adds another 3 times 10 to the 46 joules, similar to an ordinary supernova, because the core collapse physics at the moment of implosion is broadly comparable. The total energy budget is therefore roughly 4 to 6 times 10 to the 46 joules, somewhat higher than a standard supernova, primarily because the black hole formation process can be slightly more energetically efficient than neutron star formation, and because the accretion disk extracts additional energy from the infalling material. Let us be precise about where hypernovae sit in the hierarchy. They exceed ordinary supernovae in kinetic energy by factors of roughly 10 to 100. They produce jets that can carry additional energy comparable to or exceeding the spherical component. Their total energy budgets approach but do not dramatically exceed those of standard supernovae when neutrino emission is included. They are transitional objects more violent than ordinary stellar death, but still constrained by the same fundamental physics of gravitational collapse and the available mass energy of the progenitor star. Here is the critical point. The kinetic energy of a hypernova, 10 to the 45 to 10 to the 46 joules, is extraordinary. But when a hypernova's jets are strong enough, narrow enough, and sustained long enough to break free of the stellar envelope and beam their energy directly toward a distant observer, the result is something that appears to transcend everything we have discussed. The observer does not see a slightly more energetic supernova. The observer sees something that appears to release 10 to the 47 joules or more in pure electromagnetic radiation within seconds. Something so bright it momentarily outshines the combined light output of every galaxy within billions of light years. That something is a gamma-ray burst, and it occupies a category entirely its own. The hypernova is the launching pad. The collapsar mechanism, the rapidly rotating core, the accretion disk, the magnetic field amplification, all of these elements combine to create the conditions from which a gamma-ray burst can emerge. But the hypernova itself is not the gamma-ray burst. The hypernova is the spherical component visible from any angle. The gamma-ray burst is what happens when the jet survives, punches through, and delivers its concentrated payload of relativistic energy along a narrow corridor of space that happens by cosmic accident to include a small blue planet with instruments pointed in the right direction. The hypernovae we have catalogued represent explosions of genuinely exceptional violence. They carry 10 to 100 times the kinetic energy of standard supernovae. They forge heavy elements through nucleosynthetic pathways unavailable in ordinary stellar death. They reshape the chemical evolution of galaxies, particularly in the early universe where their occurrence rate was likely higher. They demonstrate that the collapsar mechanism operates across a range of parameters, producing a spectrum of explosion energies that bridges the gap between conventional supernovae and the most extreme observed phenomena. But they are not the most powerful explosion the universe has produced. The energy hierarchy established across these first two sections is clear. Ordinary supernovae release approximately 10 to the 44 joules in kinetic energy, capped by the physics of neutron star formation. Hypernovae release 10 to the 45 to 10 to the 46 joules, boosted by black hole formation and jet-driven dynamics. Each level represents a genuine escalation, a rarer, more demanding set of progenitor conditions, producing a measurably more violent outcome. The next level does not merely continue this escalation, it shatters it. The most powerful observed explosions exceed hypernovae, not by a factor of 10 or 100, but by factors that render even the hypernova, that already extraordinary event, a subordinate phenomenon. The jet, which in a hypernova contributes a significant but supplementary fraction of the total energy, becomes the dominant feature. The spherical explosion becomes the footnote. The energy concentrated into that narrow relativistic beam, when viewed from the right angle, produces measured luminosities so extreme that for decades scientists refused to believe the numbers could possibly be correct. They were correct. And the story of how we proved it against resistance, against disbelief, against 3 decades of theoretical confusion, is the story of the most powerful explosion ever directly observed in the universe. The satellites that discovered the most powerful explosions in the universe were not looking for them. They were looking for nuclear weapons. In the early 1960s, the United States, the Soviet Union, and the United Kingdom signed the Partial Nuclear Test Ban Treaty, prohibiting nuclear detonations in the atmosphere, in outer space, and underwater. Compliance verification became a priority. The American military needed eyes in orbit, instruments capable of detecting the telltale gamma radiation signature of a clandestine nuclear blast conducted above the atmosphere, where seismic monitors on the ground would be. Useless. The solution was the Vela satellite program. Between 1963 and 1970, 12 Vela satellites were launched in pairs, each carrying gamma-ray detectors, X-ray sensors, and neutron counters optimized to recognize the double flash signature of a nuclear detonation in space. On July 2nd, 1967, the Vela 3 and Vela 4 satellites registered something unexpected. A brief, intense pulse of gamma radiation swept across their detectors. The signal did not match the signature of a nuclear weapon. The flash was too short, the spectral profile was wrong, and crucially, timing analysis between the two satellites indicated the source was not near Earth. The gamma rays had arrived from deep space from a direction that pointed away from our planet, away from the Sun, away from anything in the solar system. The analysts at Los Alamos National Laboratory flagged the detection but could not explain it. Over the following years, the Vela satellites recorded 15 more of these mysterious gamma-ray flashes. Each one arrived without warning, lasted between a fraction of a second and roughly 30 seconds, and appeared to originate from a random direction in the sky. No two came from the same location. The sources were not repeating. Whatever was producing these bursts was doing so once and then going silent forever. The data remained unpublished for 6 years. In 1973, Ray Klebsadel, Ian Strong, and Roy Olson published the observations in a landmark paper in the Astrophysical Journal, announcing the detection of 16 cosmic gamma-ray bursts of unknown origin. The paper was measured, cautious, and technical. Its impact was seismic. Within months, theoretical astrophysicists around the world began proposing explanations for these mysterious flashes. What followed was one of the longest and most contentious debates in the history of modern astronomy. The central problem was distance. Gamma-ray detectors in the 1970s and 80s could tell you roughly when a burst occurred and approximately which direction it came from, but they could not measure how far away the source was, and distance was everything. If gamma-ray bursts originated within our own galaxy at distances of thousands to tens of thousands of light-years, then the energy required to produce the observed brightness was large but not extraordinary. Dozens of known astrophysical processes could potentially account for them. Neutron star quakes, magnetic reconnection events on stellar surfaces, comets impacting compact objects. The list of viable models was long and varied. But if the bursts came from cosmological distances from galaxies billions of light-years away, then the energy implied by their apparent brightness became almost incomprehensible. The same observed brightness at 1,000 times the distance demands 1,000,000 times the intrinsic luminosity. At cosmological distances, gamma-ray bursts would need to release more energy in seconds than our Sun produces in its entire 10 billion-year lifetime. That possibility seemed so extreme that many respected scientists simply refused to consider it. The debate crystallized in 1995 at a public scientific discussion deliberately modelled on the famous Shapley-Curtis debate of 1920, which had concerned whether spiral nebulae were part of the Milky Way or separate galaxies in their own right. In this modern echo, astronomer Donald Lamb argued that gamma-ray bursts originated within the halo of our galaxy distant, but not absurdly so. Bohdan Paczynski argued that they were cosmological, originating in galaxies across the observable universe. Both presented compelling evidence. Neither could deliver a decisive blow. The field remained deadlocked. The frustration by that point had accumulated over more than 2 decades. Since the publication of Klebsadel's original paper in 1973, theorists had proposed well over 100 models to explain gamma-ray bursts. The list ranged from plausible to exotic: neutron star quakes, collisions between comets and neutron stars, the evaporation of primordial black holes, phase transitions in neutron star interiors, flares on nearby stars, and dozens more. Without a distance measurement, none could be definitively ruled out. The field had become, in the words of one frustrated observer, a subject where the number of theoretical models exceeded the number of observational constraints by a comfortable margin. Entire careers had been spent studying these objects, and after 22 years the most basic question about them, how far away are they, remained unanswered. Meanwhile, a critical piece of evidence had quietly strengthened the cosmological case. The BATSI instrument aboard NASA's Compton Gamma Ray Observatory, operational since 1991, had by the mid-90s recorded well over 1,000 gamma-ray bursts. Their distribution across the sky was strikingly uniform. The bursts came from every direction, with no preference for the plane of the Milky Way, no concentration toward the galactic center, no clustering around any known galactic structure. A population of objects within our galaxy would almost inevitably show some correlation with the galaxy's disk or halo geometry. The isotropy of the Batsy catalogue was exactly what you would expect from sources scattered uniformly across the distant universe. It was powerful circumstantial evidence, but it was not proof. Clever galactic halo models could reproduce the observed uniformity if the halo was large enough and the source distribution was carefully tuned. The models required certain assumptions that struck many physicists as contrived, but for scientists who found the cosmological energy requirements physically unacceptable, contrivance was preferable to impossibility. The energy numbers at cosmological distances were simply too large for some researchers to swallow. They looked at the figures and saw not a discovery, but an error waiting to be found. What the field needed was not another theoretical argument. It needed a single, unambiguous measurement of distance. Everything hinged on that. The stalemate was broken not by theoretical argument, but by a single observation from a satellite that almost was not built. Beppo Sachs was an Italian-Dutch X-ray astronomy satellite launched in April 1996. It carried a set of wide-field cameras capable of detecting gamma-ray bursts and, critically, an array of narrow-field X-ray telescopes that could be pointed toward the burst location within hours. This combination allowed something no previous instrument could achieve: rapid, precise localization of a gamma-ray burst's position on the sky, accurate enough for optical telescopes on the ground to search for a visible counterpart. On February 28, 1997, Beppo Sachs detected GRB 970228. Within 8 hours, its X-ray telescopes identified a fading X-ray source at the burst position. Optical telescopes on the ground found a fading visible light counterpart, the first optical afterglow of a gamma-ray burst ever detected. Deep imaging revealed that the afterglow sat within a faint, distant galaxy. Spectroscopic measurements of that galaxy yielded a redshift of approximately 0.7, placing it roughly 8 billion light-years from Earth. The cosmological camp had won. Gamma-ray bursts were extragalactic. They came from across the observable universe, and that meant the energy figures were real. Within months, a second burst confirmed the result beyond doubt. GRB 970508, detected on May 8, 1997, produced an optical afterglow whose spectrum directly yielded a redshift of 0.835, approximately 7 billion light-years. The measurement was unambiguous. The burst had originated in a galaxy so distant that its light had been travelling for more than half the current age of the universe. At that distance, the observed brightness implied an isotropic equivalent energy output exceeding 10 to the 52 ergs. Let us unpack what isotropic equivalent energy means, because this quantity is central to understanding why gamma-ray bursts top the cosmic explosion hierarchy. When astronomers detect a gamma-ray burst and measure its brightness, the amount of energy arriving at Earth's detectors per second, they can calculate the total energy the burst would need to have released if it radiated equally in all directions. This is a straightforward calculation. You measure the flux at Earth's distance, multiply by the surface area of a sphere centered on the burst with a radius equal to the burst distance, and you get the total energy assuming isotropic emission. This isotropic equivalent energy is almost certainly an overestimate of the true total energy, because gamma-ray bursts do not radiate isotropically. Their energy is concentrated into narrow jets. But the isotropic equivalent figure serves as a robust upper bound that requires no assumptions about jet geometry. It represents the maximum possible energy consistent with the observations. For early bursts with measured redshifts, the isotropic equivalent energies routinely exceeded 10 to the 52 ergs. Some approached 10 to the 53. These numbers were staggering, exceeding the total energy output of ordinary supernovae by factors of hundreds to thousands. concentrated into gamma radiation emitted over mere seconds. The field accelerated rapidly after Beppo-Sax's breakthrough. NASA's SWIFT satellite, launched in November 2004, was purpose-built to detect gamma-ray bursts and slew its onboard X-ray and ultraviolet optical telescopes toward the burst position within seconds. SWIFT detected hundreds of bursts, measuring their positions, redshifts, and afterglow properties with unprecedented precision. The data confirmed and extended the picture established by Beppo-Sax. Long-duration gamma-ray bursts, those lasting longer than approximately 2 seconds, consistently originated in star-forming regions of distant galaxies, often at redshifts exceeding 1, corresponding to distances of billions of light-years. Their host galaxies were typically small, irregular, and metal-poor, exactly the environments where the collapsar progenitors described in Part 2 would be most common. Then came the Fermi Gamma-Ray Space Telescope, launched in June 2008. Fermi carried the Large Area Telescope, sensitive to gamma rays at energies far exceeding previous instruments, and the Gamma Ray Burst Monitor, capable of detecting bursts across nearly the entire sky. Fermi's capabilities opened a new window on gamma-ray burst energetics, revealing emission at energies reaching tens of billions of electron volts, photons individually carrying more energy than anything a particle accelerator on Earth had produced at that time. On September 16, 2008, Fermi detected GRB 080916c. The burst originated at a redshift of approximately 4.35, corresponding to a distance of roughly 12.2 billion light-years. Light from this explosion had been travelling for more than 12 billion years. It was emitted when the universe was barely 1.5 billion years old. The isotropic equivalent energy was measured at approximately 8.8 times 10 to the 54 ergs, written out in joules. That is roughly 8.8 times 10 to the 47 joules. To contextualize this figure, if you could convert the entire mass of our Sun into pure energy using Einstein's mass-energy equivalence, you would obtain approximately 1.8 times 10 to the 47 joules. GRB 080916c appeared to release nearly 5 solar masses worth of pure energy in gamma radiation alone, within a span of roughly 60 seconds. For a brief window during its peak emission, this single event was more luminous than every star in the observable universe combined. Every galaxy, every quasar, every pulsar, every active galactic nucleus, all of it summed together, could not match the instantaneous radiative output of this one dying star, 12 billion light-years away. The number defied intuition. It defied, for some, belief. But the measurements were solid, cross-checked across multiple instruments, and consistent with the established distance. GRB 080916c held the energy record for over a decade. Then October 9, 2022, produced an event that redefined what astronomers thought possible. GRB 2210009a erupted from a source approximately 2.4 billion light-years away, much closer than GRB 080916c, but still an enormous cosmological distance. Its proximity, combined with its intrinsic power, created an observed brightness so extreme that it overwhelmed nearly every gamma-ray detector in orbit. The Fermi Gamma-Ray Burst Monitor saturated. The Swift Burst Alert Telescope saturated. Even instruments not designed to detect gamma-ray bursts registered the signal. The burst ionized Earth's upper atmosphere measurably, affecting radio wave propagation on the planet's surface, a direct physical effect from an explosion 2.4 billion light-years away. The isotropic equivalent energy of GRB 221009a exceeded 10 to the 54 ergs. Its prompt gamma-ray emission lasted over 300 seconds, far longer than typical long-duration bursts. The afterglow was detected across the entire electromagnetic spectrum radio, infrared, optical, ultraviolet, X-ray, and gamma-ray, and remained observable for months. Statistical analysis indicated that a burst this bright striking Earth from this distance occurs approximately once every 10,000 years. Astronomers informally named it the Boat, the brightest of all time, a designation that captured both its significance and the field's astonishment. The experience of detecting the Boat was unlike anything the gamma-ray burst community had encountered. Automated alert systems fired simultaneously from multiple satellites, flooding astronomers' inboxes and triggering pagers across every time zone. Within minutes, researchers examining the incoming telemetry realized something was wrong with their data, not wrong in the sense of a malfunction, but wrong in the sense that the numbers exceeded the range their instruments were designed to record. The Fermi Gamma-Ray Burst Monitor, built to measure the brightest events in the universe, returned saturated data. The Swift Burst Alert Telescope, designed with generous dynamic range for exactly this scenario, also saturated. Among the few instruments that captured the burst's full profile without saturating was the CONUS detector aboard the WIND spacecraft, orbiting the Sun-Earth Lagrange point, an instrument whose design for high-rate events proved prescient. Reconstructing the burst's true peak brightness required painstaking cross-referencing between the handful of unsaturated instruments and careful analysis of the saturated data from those that had been overwhelmed. The effects extended beyond orbiting observatories. The gamma-ray flux ionized Earth's upper ionosphere so significantly that very low-frequency radio monitoring stations' instruments designed to study lightning propagation and geomagnetic disturbances, not astrophysical explosions, recorded a measurable shift in the ionospheric electron density. The disturbance resembled the signature of a moderate solar flare, but the source was not our Sun. The source was a dying star in a galaxy so distant that its light had been traveling for roughly a fifth of the age of the universe. An explosion 2.4 billion light-years away had physically altered the electrical properties of our planet's atmosphere. The effect was brief and harmless, but its existence underscored a point that no amount of abstract energy figures could convey as viscerally. These events are not merely distant curiosities. They are physical phenomena whose reach extends across cosmological distances to touch the very planet on which we stand. In the days that followed, the optical afterglow proved bright enough for amateur astronomers with modest backyard telescopes to image an almost unprecedented occurrence for a gamma-ray burst, which typically requires professional-grade instruments to detect invisible light. Observatories on every continent trained their instruments on the fading source. Data accumulated at a rate that overwhelmed the normal pace of astronomical publication. Preprint servers filled with analyses. Telescope time was reallocated on an emergency basis for the specialists who had spent careers studying these events. The Boat was the kind of observation that occurs perhaps once in a scientific lifetime, an event so far beyond the normal range of their instruments that it forced a fundamental reassessment of what those instruments needed to be, capable of measuring. The Boat provided the richest dataset ever collected for a single gamma-ray burst. Its afterglow evolution, jet structure, and energy dissipation were tracked in real time across dozens of observatories worldwide. The observations confirmed theoretical predictions about jet dynamics with remarkable fidelity, including the expected transition from ultra-relativistic to sub-relativistic expansion as the jet decelerated against the surrounding interstellar medium. Now we must address the true energy of these events by applying the beaming correction. The isotropic equivalent energy figures quoted above assume the burst radiates equally in all directions. They do not. The gamma-ray emission originates from a narrow jet, and the jet opening angle determines what fraction of the sky receives the concentrated energy. For well-studied bursts where afterglow observations reveal a characteristic steepening called a jet break in the light curve, the jet opening half angle can be measured. Typical values range from approximately 2 to 20 degrees, with a median around 5 to 6 degrees. A jet with an opening half angle of 5 degrees covers a solid angle of approximately 2.4 times 10 to the negative 2 steradians. The full sky encompasses 4 pi steradians, or roughly 12.6 steradians. The fraction of the sky illuminated by the jet is therefore about 1/500th. The true energy radiated in gamma rays is approximately 1/500th of the isotropic equivalent value. For a burst with an isotropic equivalent energy of 10 to the 54 ergs, the beaming-corrected gamma ray energy comes to roughly 2 times 10 to the 51 ergs, approximately 2 times 10 to the 44 joules. This correction is dramatic. It reduces the gamma ray energy from a seemingly impossible figure to one that, while still enormous, can be accommodated by the collapsar model's energy budget. But the gamma ray emission represents only one component of the jet's total energy output. The relativistic material in the jet also carries kinetic energy. The energy of bulk motion of baryonic matter accelerated to near light speed. This kinetic energy is revealed through the afterglow, which is produced as the jet decelerates against the external medium and converts its bulk kinetic energy into radiation. Detailed afterglow modelling for the best studied bursts indicates that the jet's total energy, combining radiative and kinetic components, typically falls in the range of 10 to the 51 to 10 to the 52 ergs, or roughly 10 to the 44 to 10 to the 45 joules. Remarkably, when the beaming correction is applied across a sample of many bursts, the true total jet energies cluster around a relatively narrow range, suggesting a characteristic energy scale of approximately 10 to the 51 ergs. This clustering, sometimes called the Frail relation, after Dale Frail, who first demonstrated it in 2001, implies that gamma-ray burst central engines produce a roughly standard total energy output, and the wide variation in observed brightness results primarily from differences in jet opening angles. Narrower jets produce apparently brighter bursts that are visible to fewer observers. Wider jets produce dimmer bursts visible to more observers. The intrinsic energy is approximately constant. Even after beaming correction, the jet energy of a gamma-ray burst exceeds the kinetic energy of an ordinary supernova by 1 to 2 orders of magnitude, and the jet is only part of the total event. The collapsar also produces a quasi-spherical hypernova explosion, the disruption of the stellar envelope described in Part 2, which carries additional kinetic energy of approximately 10 to the 45 to 10 to the 46 joules. The formation of the central black hole releases gravitational binding energy comparable to neutron star formation, roughly 3 times 10 to the 46 joules, most of which escapes as neutrinos. Gravitational wave emission adds a further contribution, though for collapsars this component is expected to be smaller than for compact binary mergers. The total energy budget of a gamma-ray burst event summing every component sits at approximately 10 to the 46 to 10 to the 47 joules. This places it at the absolute summit of observed explosive phenomena. No other directly detected event combines this total energy with this concentration of power energy per unit time. The peak luminosity of a gamma-ray burst, even after beaming correction, exceeds that of a supernova by factors of millions. The energy is released in seconds rather than weeks. The physical mechanism accretion onto a stellar mass black hole operates at the highest efficiency of any known energy conversion process, short of matter-antimatter annihilation. The internal physics of the jet deserves examination because it reveals how the observed gamma-ray emission is actually produced. The central engine, the accreting black hole, does not emit gamma rays directly. Instead, it launches a relativistic outflow whose internal dynamics generate the observed radiation through a multi-step process. The outflow is irregular. The central engine operates sporadically, ejecting shells of material at varying velocities over the duration of the burst. Faster shells catch up with slower ones at large distances from the central engine, producing internal collisions called internal shocks. At the shock front, electrons are accelerated to ultra-relativistic energies by the shock's electromagnetic fields. These accelerated electrons emit gamma rays through 2 primary mechanisms: synchrotron radiation, produced as electrons spiral around magnetic field lines, and inverse Compton scattering, in which electrons transfer their energy to lower energy photons, boosting them to gamma ray wavelengths. The prompt gamma ray emission, the initial burst detected by orbiting satellites, arises from these internal shocks. The afterglow emission arises from a different process. As the jet plows into the surrounding interstellar medium, it drives an external shock, a blast wave that sweeps up ambient material and decelerates the jet over days to months. The external shock accelerates electrons and generates magnetic fields, producing synchrotron radiation that spans the electromagnetic spectrum from radio to X-ray. The afterglow fades gradually as the jet decelerates, and its energy is radiated away, providing a window into the jet's total kinetic energy content. Monitoring the afterglow's brightness across multiple wavelengths and its evolution over time allows astronomers to reconstruct the jet's opening angle, Lorentz factor, energy, and the density of the surrounding medium. The Lorentz factors involved in gamma-ray burst jets are extreme. Measured values range from approximately 100 to over 1,000. A Lorentz factor of 300 means the jet material moves at 99.9994% of the speed of light. At these velocities, relativistic effects dominate. Time dilation compresses the observed duration of emission from the jet. Doppler boosting amplifies the observed brightness by enormous factors for observers within the jet cone. The combination of these effects explains how a finite energy budget can produce the apparently infinite luminosities seen in the brightest bursts. We must now clearly distinguish long-duration gamma-ray bursts from their shorter cousins. Gamma-ray bursts divide observationally into two classes, based on duration. Long-duration bursts last longer than approximately 2 seconds and are associated with the core collapse of massive stars, the collapsar mechanism. Short-duration bursts last less than approximately 2 seconds and originate from the merger of compact binary systems, typically two neutron stars or a neutron star and a black hole. The short burst origin was confirmed spectacularly on August 17, 2017, when the LIGO and Virgo gravitational wave detectors registered the signal of two merging neutron stars designated GW170817, and the Fermi satellites simultaneously detected a short gamma-ray burst, GRB 170817A, from the same location. This coincident detection, followed by extensive electromagnetic observations across all wavelengths, provided irrefutable proof that at least some short gamma-ray bursts arise from neutron star mergers. Neutron star mergers are extraordinary events in their own right. GW 170817 released approximately 3 solar masses of energy in gravitational waves, roughly 5.4 times 10 to the 47 joules. This exceeds the electromagnetic energy of any gamma-ray burst. However, gravitational wave energy interacts with matter so weakly that it passes through the universe with negligible physical effect. No material is ejected by the gravitational waves themselves. No shockwave propagates. The energy is real but effectively invisible to all detection methods except gravitational wave interferometers. The electromagnetic output of short gamma-ray bursts is generally lower than that of the most powerful long-duration events. The isotropic equivalent energies of short bursts typically range from 10 to the 49 to 10 to the 52 ergs substantial, but below the 10 to the 54 ergs reached by exceptional long bursts. The total jet energy after beaming correction is correspondingly lower. Additionally, neutron star mergers do not produce the associated hypernova explosion that accompanies collapsars, though they do generate a distinctive thermal emission called a kilonova, powered by the radioactive decay of heavy elements synthesized in the neutron-rich merger ejector. Short gamma-ray bursts and their associated kilonovae are profoundly important for astrophysics. They are the primary sites of rapid neutron capture nucleosynthesis, the process responsible for creating roughly half of all elements heavier than iron, including gold, platinum, and uranium. The detection of GW 170817 and its kilonova confirmed this decades-old theoretical prediction with direct observational evidence. But in terms of total explosive energy in the electromagnetic channel, short bursts do not surpass the most powerful long-duration gamma-ray bursts from collapsing massive stars. The evidence converges from every direction. Decades of observation across the electromagnetic spectrum, hundreds of detected bursts with measured distances, detailed afterglow modelling confirming jet energetics, spectroscopic identification of associated hypernovae in the nearest events, statistical analysis of the burst population confirming the energy clustering around 10 to the 51 ergs after beaming correction, theoretical models grounded in general relativity and magnetohydrodynamics that reproduce the observed properties with quantitative fidelity. The conclusion is not ambiguous. It does not depend on which measurement you emphasize or how you frame the question. By the metric of total energy released in a single explosive event, combining jet energy, hypernova kinetic energy, neutrino emission, and gravitational wave output, long-duration gamma-ray bursts from the collapse of rapidly rotating massive stars into black holes are the most powerful explosions ever directly observed in the universe. No supernova reaches their energy, no hypernova matches their concentrated power, no short gamma-ray burst from a neutron star merger surpasses their electromagnetic output. No tidal disruption event, no magnetar flare, no active galactic nucleus outburst observed to date has combined this total energy release with this explosive timescale. Gamma-ray bursts stand alone at the summit of the observed cosmic violence hierarchy, but stating that they occupy the summit raises a question that demands an answer. Why? Why do gamma-ray bursts represent the ceiling? Is it coincidence that we have never observed anything more powerful? Or is there a reason embedded in the laws of physics themselves that prevents the universe from producing something more extreme? The answer lies not in what the universe has done, but in what the universe is permitted to do. And that boundary, that hard limit on cosmic violence, is written into the deepest structure of physical law. The universe is not infinitely violent. This statement might seem obvious, but its implications are profound, and its enforcement is absolute. Every physical system that has ever existed, every star, every black hole, every colliding galaxy operates within boundaries it did not choose and cannot overcome. These boundaries are not suggestions. They are consequences of the mathematical structure of reality itself, woven into the equations that govern how matter behaves, how energy moves, and how space-time curves under extreme conditions. Gamma-ray bursts do not sit at the top of the cosmic explosion hierarchy by accident. They sit there because the physics of energy production and release reaches its practical maximum in the collapsar mechanism, and no observed phenomenon has found a way around the constraints that limit it. Understanding why requires examining those constraints one by one, because each represents a wall that the universe cannot climb past, no matter how massive the star, how rapid the rotation, or how intense the magnetic field. The first constraint is the efficiency of gravitational energy extraction. The fundamental power source for a gamma-ray burst is not nuclear fusion, not matter-antimatter annihilation, not some exotic quantum process. It is gravity. Specifically, it is the conversion of gravitational potential energy into kinetic energy, radiation, and magnetic fields as material falls toward and spirals into a black hole. This conversion process operates through the accretion disk, the swirling ring of superheated material that forms around the black hole when the collapsing stellar core carries sufficient angular momentum. The efficiency of this conversion is governed by general relativity. For a non-rotating Schwarzschild black hole, material spiraling inward through an accretion disk can convert approximately 5.7% of its rest mass energy before crossing the innermost stable circular orbit and plunging past the event horizon. Beyond that orbit, no further energy can be extracted. The material falls freely into the black hole, carrying its remaining energy with it irretrievably. For a maximally rotating Kerr black hole, one spinning at the theoretical limit permitted by general relativity, the innermost stable orbit moves closer to the event horizon, and the extraction efficiency climbs to approximately 42%. This is an extraordinary figure. Nuclear fusion in stellar cores converts less than 1% of rest mass energy into radiation. Accretion onto a spinning black hole is roughly 50 times more efficient than the process that powers every star in the universe. But 42% is not 100%. More than half of the infalling material's rest mass energy is swallowed by the black hole, regardless of the disk's configuration. And the accretion disk in a collapsar contains a finite amount of material, at most a few solar masses, determined by the mass of the progenitor star's core minus what goes directly into forming the black hole. The maximum energy extractable through disk accretion is therefore approximately 42% of a few solar masses multiplied by the speed of light squared. For 3 solar masses of accreted material at maximum efficiency, this yields roughly 2.3 times 10 to the 47 joules. That figure represents the absolute theoretical ceiling for energy extraction through accretion in a single collapsar event. Observed gamma-ray bursts release total energies at or somewhat below this limit. No violation has ever been recorded. The Blandford-Znaiec mechanism offers a supplementary energy channel. A spinning black hole immersed in a strong magnetic field, as would exist in a collapsar environment, can transfer rotational energy to the surrounding plasma through electromagnetic coupling between the black hole's ergosphere and the external magnetic field lines threading the event horizon. This process can extract up to approximately 29% of the black hole's total rotational energy. For a stellar mass black hole of 10 solar masses spinning near the maximum rate, the available rotational energy is roughly 10 to the 47 joules, and the Blandford-Znaiec process can tap roughly 3 times 10 to the 46 joules of that reservoir. This is significant but not unlimited. The rotational energy depends on the black hole's mass and spin, both of which are finite quantities set by the progenitor star's properties. And the rate at which the Blandford-Znaiec process can extract energy depends on the magnetic field strength threading the horizon, which itself is limited by the surrounding plasma conditions. If the magnetic pressure exceeds the gas pressure of the surrounding material, the field configuration becomes dynamically unstable and dissipates. This instability imposes a natural ceiling on the magnetic field strength and, consequently, on the jet power. The second major constraint is the mass of the progenitor star. Everything about a gamma-ray burst's energy budget traces back to how much material is available to fuel the central engine. More massive progenitors provide more massive cores, which form more massive black holes with more massive accretion disks. In principle, a more massive progenitor should produce a more energetic burst. But stellar masses are not unlimited. The most massive stars observed in the contemporary universe reach approximately 150 to 200 solar masses. Above this range, stars encounter the Eddington, limit the point at which radiation pressure generated by the star's own luminosity exceeds the gravitational force holding the star together. A star above the Eddington limit literally blows itself apart, shedding material through radiation-driven winds until its mass drops below the critical threshold. This self-regulating mechanism prevents stars from growing indefinitely. You cannot simply build a more massive star and expect a proportionally more energetic explosion. Nature enforces a ceiling on the fuel supply. Theoretical models do allow for more massive stars in the early universe, when metallicities were lower and stellar winds correspondingly weaker. Population 3 stars the hypothetical first generation of stars, formed from pristine hydrogen and helium, with virtually no heavier elements may have reached several hundred solar masses or more. Their deaths could theoretically have produced collapsar events with somewhat larger energy budgets than anything occurring in the modern universe. But even these primordial giants were limited. Their cores, while massive, could only form black holes of finite mass with accretion disks of finite extent. The energy ceiling is higher for these hypothetical objects, but not infinitely so. And crucially, no population 3 gamma-ray burst has been directly observed. The constraint on observed explosions remains set by the most extreme events we have actually detected. The third constraint involves jet collimation and stability. The extreme apparent brightness of gamma-ray bursts arises partly from their energy being concentrated into narrow jets rather than radiated uniformly across the sky. A narrower jet focuses more energy per unit solid angle, creating a brighter signal for observers within the beam. One might ask, could a jet be made arbitrarily narrow, concentrating its energy into an infinitesimally thin beam and creating an arbitrarily bright burst? It cannot. Magnetohydrodynamic simulations of relativistic jet formation show that jets with opening half angles below approximately 1 degree become unstable. Kink instabilities, helical distortions of the jet's magnetic structure, grow rapidly in extremely narrow outflows, disrupting the jet's coherence before it can propagate far enough to escape the stellar envelope. The jet fragments, dissipates its energy internally, and fails to produce an observable gamma-ray burst. This imposes a lower bound on the jet opening angle, and consequently an upper bound on how concentrated the beam can become. The brightest possible gamma-ray burst is constrained not just by the total energy available, but by the minimum solid angle over which that energy can be delivered. The fourth constraint is the accretion timescale. The duration of a gamma-ray burst is set by how long the central engine remains active, which is determined by how long material continues falling onto the black hole through the accretion disk. For typical collapsar progenitors, this timescale ranges from a few seconds to several hundred seconds, depending on the mass and structure of the stellar core. Ultra-long gamma-ray bursts lasting thousands of seconds have been detected, but these appear to involve progenitors with exceptionally extended envelopes, blue supergiants rather than compact Wolf-Rayet stars, and their average luminosities are typically lower than shorter, more intense events. The total energy remains comparable because a longer duration at lower luminosity can match a shorter duration at higher luminosity. The central engine's total energy budget is set by the available mass and the extraction efficiency, not by how quickly or slowly it operates. These four constraints, accretion efficiency, progenitor mass, jet stability, and accretion timescale, work together to define an envelope of maximum possible energy for any single collapsar event. That envelope sits at approximately 10 to the 47 joules total energy release, with jet energies of approximately 10 to the 44 to 10 to the 45 joules. The most powerful observed gamma-ray bursts cluster near this theoretical ceiling. They are not outliers defying physics. They are the expected outcome when every parameter stellar mass, core rotation, magnetic field amplification, jet collimation simultaneously approaches its physical maximum. The universe permits gamma-ray bursts to exist, but it permits them only barely. Push any single parameter higher, and the system fails. The star explodes prematurely before core collapse. The disk fragments before the jet can form. The jet disrupts before it escapes the star. The black hole swallows everything before energy can be radiated. The window of conditions that produces a successful gamma-ray burst is narrow, and the energy it permits is finite. With the physics of the ceiling established, we can now examine whether any other observed or hypothetical phenomenon challenges gamma-ray bursts for the title of most powerful explosion. Tidal disruption events occur when a star passes too close to a supermassive black hole, one containing millions to billions of solar masses, and is torn apart by the differential gravitational pull across its diameter. The resulting debris forms an accretion disk around the supermassive black hole, producing a luminous flare that can last weeks to months. In some cases, relativistic jets are launched, creating events that superficially resemble gamma-ray bursts. The jetted tidal disruption event, Swift-J 1000, 644 plus 57, detected in 2011, produced an isotropic equivalent X-ray luminosity rivaling that of a gamma-ray burst. However, tidal disruption events are not single explosive releases of energy. They are prolonged accretion episodes lasting months to years. The total radiated energy, approximately 10 to the 40, 4 to 10 to the 46 joules, is released over timescales thousands of times longer than a gamma-ray burst. The peak luminosity is lower, the energy per unit time is dramatically lower. A tidal disruption event is powerful in aggregate, but it is not an explosion in the same sense as a gamma-ray burst. It is the difference between a controlled demolition and a detonation. Magnetar giant flares represent another candidate. Magnetars, neutron stars with magnetic fields exceeding 10 to the 15 Gauss, can undergo catastrophic magnetic reconnection events that release enormous energy in fractions of a second. The most powerful observed magnetar flare, from SGR 1806-20 on December 27, 2004, released approximately 10 to the 39 joules of electromagnetic energy in about 0.2 of a second. The peak luminosity was extraordinary for that brief instant, but the total energy was roughly 10 million times less than a gamma-ray burst. Magnetar flares are impressive on neutron star scales. On the cosmic violence hierarchy, they do not compete. Active galactic nuclei powered by accretion onto supermassive black holes produce the most luminous sustained energy output in the universe. Some quasars radiate at luminosities exceeding 10 to the 40 watts, maintained over millions of years. The total energy released over an active galactic nucleus's lifetime can reach 10 to the 54 joules or more, vastly exceeding any gamma-ray burst. But this energy is released over geological timescales, not in a single explosive event. An active galactic nucleus is a furnace, not a bomb. No single AGN flare or outburst observed to date has concentrated more energy into an explosive timescale than a long-duration gamma-ray burst. What about gravitational wave events? The merger of two stellar mass black holes, such as the event GW 150914 detected by LIGO in September 2015, released approximately 3 solar masses of energy in gravitational waves, roughly 5.4 times 10 to the 47 joules. This exceeds the total electromagnetic energy of any gamma-ray burst. The figure is genuine and confirmed by direct detection. However, gravitational waves interact with matter so feebly that this energy passes through the entire universe with effectively zero physical impact. No material is ejected, no shockwave propagates, no electromagnetic radiation is produced. A binary black hole merger in vacuum is energetically extraordinary, but observationally silent in every wavelength except gravitational waves. It is an event of immense energy, but it is not an explosion. No destruction of a progenitor object occurs, no ejector are launched, and no surrounding environment is disrupted. Placing it on the same scale as supernovae and gamma-ray bursts conflates fundamentally different categories of energy release. Neutron star mergers, as discussed in Part 3, produce both gravitational waves and electromagnetic explosions. GW 170817 released approximately 5.4 times 10 to the 47 joules in gravitational waves and generated a short gamma-ray burst with electromagnetic energy far below the most powerful long-duration events. The kilonova that followed, powered by radioactive decay of newly synthesized heavy elements, added additional radiated energy over days and weeks. But the total electromagnetic explosive output remained below the threshold set by the most powerful collapsers. One clarification is essential at this point because it addresses a misconception so widespread that leaving it uncorrected would undermine the entire framework of this story. The Big Bang was not an explosion. It is routinely described as one in popular media, in casual conversation, and even in some educational materials. This description is fundamentally incorrect in a way that matters for understanding cosmic energy scales. An explosion is an event that occurs within existing space. Material expands outward from a central point into the surrounding volume. There is a before and an after. There is a location where the explosion happened and other locations where it did not. The Big Bang was none of these things. It was the expansion of space itself. There was no pre-existing void into which material flew. There was no central point from which matter radiated outward. Every point in the universe was and remains the center, because the expansion is a property of the fabric of space-time, rather than the motion of objects through that fabric. The Big Bang created the conditions under which all subsequent structure, energy release, and cosmic evolution occurred. But it belongs to a categorically different class of physical phenomenon than supernovae hypernovae, or gamma-ray bursts. It must not be placed on the same ranking. It is not a competitor for the title of most powerful explosion, because it is not an explosion at all. With hypothetical alternatives addressed, we can now enter clearly speculative territory labelled as such. Could anything in the universe theoretically exceed a gamma-ray burst? Pair instability supernovae are predicted to occur when extremely massive stars, those with helium core masses between roughly 65 and 130 solar masses, undergo a thermonuclear detonation, triggered by the production of electron-positron pairs in the stellar core. The pair production process removes pressure support from the core, triggering a contraction that ignites explosive thermonuclear burning powerful enough to completely unbind the star. No remnant is left behind, no neutron star, no black hole. The entire star is converted into expanding debris and radiation. Theoretical models predict kinetic energies up to 10 to the 46 joules for the most extreme pair instability events comparable to the upper range of hypernovae. Several candidate pair instability supernovae have been identified among superluminous supernovae, but none have been confirmed beyond doubt, and none have demonstrated total energies exceeding the most powerful observed gamma-ray bursts. Hypothetical exotic phenomena, such as the collapse of cosmic strings, the evaporation of primordial black holes through Hawking radiation, or the decay of metastable vacuum states, could in principle release energies far exceeding any astrophysical explosion. But none of these have been observed. They remain theoretical constructs without direct evidence. Placing them alongside confirmed gamma-ray burst measurements would violate the boundary between observation and speculation that this story has maintained throughout. The honest conclusion, drawn strictly from observed data, is that long-duration gamma-ray bursts from collapsing massive stars represent the most powerful explosive events ever directly detected by human instruments. No confirmed observation of any kind has surpassed their total electromagnetic and kinetic energy output within a single explosive episode. The theoretical framework explaining their energy production is consistent with general relativity, magnetohydrodynamics, and nuclear physics. The physical constraints limiting their energy are well understood and appear inviolable without invoking speculative new physics. There is something quietly extraordinary about this conclusion. We live in a universe that permits violence on scales that obliterate every human frame of reference. A single dying star can concentrate into a few fleeting seconds more energy than a sun-like star generates across its entire hydrogen-burning lifetime. A beam of radiation narrower than a pencil held at arm's length, when traced back across billions of light-years, connects to an event that briefly outshone the combined luminosity of every star in the observable cosmos. The temperatures in a gamma-ray burst jet exceed anything found in stellar interiors by factors of millions. The particle energies surpass those achieved by the most powerful accelerators ever built on Earth. The violence is real, measured, confirmed by instruments on 6 continents and in orbit around our planet. And yet that violence has a boundary. The universe does not permit infinite destruction. It enforces energy ceilings through the mathematics of general relativity, the nuclear physics of neutron degeneracy and black hole formation, the thermodynamics of accretion, and the magnetohydrodynamics of relativistic jet stability. These ceilings are not arbitrary. They are not imposed from outside. They emerge from the internal logic of physical law, from the same equations that govern the fall of an apple and the orbit of a planet. The universe's most extreme explosions obey the same rules as its most mundane processes. Only the numbers change. Gamma-ray bursts press against these ceilings. They represent the collapsar mechanism operating near its theoretical maximum, the most massive progenitors, the fastest core rotation, the strongest magnetic field amplification, the most efficient energy extraction. Every parameter is pushed toward its limit simultaneously. The result is an event that sits at the extreme edge of what the cosmos permits, not beyond, not even slightly beyond, exactly at the edge. This is perhaps the deepest lesson of the entire story. The universe is not chaotic. It is not random. It is not unbounded. Even in its most violent moments, it operates within a framework of law that determines what is possible and what is forbidden. The same gravity that holds you to your chair compresses stellar cores to nuclear density and launches relativistic jets across billions of light years. The same electromagnetism that lights your screen accelerates particles to within a fraction of the speed of light in the magnetic fields of a collapsar disk. The same nuclear physics that powers the sun ultimately limits how much energy a collapsing core can release. The rules are universal. The scale varies. The rules do not. We began with military satellites accidentally detecting gamma radiation from beyond our solar system. We traced the energy hierarchy from ordinary supernovae, immense but bounded by neutron star physics, through hypernovae, where rapidly rotating cores and black hole formation push kinetic energies 10 to 100 times higher. We arrived at gamma-ray bursts, where ultra-relativistic jets carry concentrated energy across cosmological distances with a power no other observed phenomenon has matched. And we examined the physics that prevents anything from climbing higher, the efficiency limits of accretion, the mass limits of stellar progenitors, the stability limits of collimated jets, the inescapable mathematics of general relativity. The answer to the question posed at the beginning of this story is not ambiguous. It is not subjective. It does not depend on definitions or framing. Long-duration gamma-ray bursts born from the gravitational collapse of rapidly rotating massive stars into black holes, powered by the most efficient energy extraction mechanism known to physics, channeled through ultra-relativistic jets that punch through the dying star and streak across the cosmos at velocities indistinguishable from light itself, are the most powerful explosions ever directly observed in the universe, measured by total energy released per event, confirmed by decades of multi-wavelength observation, explained by theoretical models grounded in the most rigorously tested frameworks in all of physics. The universe permits extraordinary violence, but it enforces hard energy ceilings, and gamma-ray bursts sit at the extreme edge of what the universe allows. They are the loudest scream the cosmos has ever produced, and the laws of physics guarantee that it cannot scream any louder.